Now, for the second question, it's unfortunate that many people didn't feel prepared to answer this because they hadn't studied in detail the vector space chapter. But in fact, you could have done this knowing things that we knew from earlier about linear independence and linear dependence. All right, so here we say P2 is the vector space of all polynomials of degree 2 or less, and let H be the span of these vectors. Now, I made the point last week, and maybe it didn't come home, is that we can consider this set of vectors as a set of column vectors. Okay. This first one, for instance, if I want to translate this into a column vector, I can write it as, it's best to put the constant one first, so I'd put 3, and then the next would be the x coefficient, which would be 1, and then the next would be the x squared coefficient, which would be minus 2. Now for the second column, the constant coefficient is minus 6. Then we'd have 0, and then we'd have 4. And then the last one would be, then this one here would be 3, 1, 0, and then 1, 1, 0. So I can write this as a set of columns like this. Now, first question, is H a subspace? Justify your answer. In fact, any span is a subspace. Any span is a subspace. That's a basic fact of vector spaces, and that comes from right here. Theorem SSS, span of a set is a subspace. This is from it was section S from the book. All right, so that's straightforward. Now, find a linearly independent set of vectors which spans H. Show your reasoning. Now, this matrix should be familiar from question 1. In fact, it is, well, I switched the rows around, but if you move the rows back, you will find that this matrix is exactly the same as this matrix. So it has the same row reduction. So it row reduces to this same matrix. And this is from question 1. I know it's going to be 1, 0, 0, 0, 1, 0, 0, 0, 1. And then it has some stuff here which I really don't care about. These columns give me the linearly independent vectors. Okay, so that means the first 3 vectors are linearly independent. This one, and this one. So in fact, I could take the first 3 polynomials, and that would be a linearly independent set, which spans H. What's the dimension of H? Dimension of H is the number of linearly independent vectors, so it's 3. Okay. I'm sorry that people had trouble with that. I think after a couple of weeks you won't have any trouble at all with problems like that. Let's look at question 4. And here's another case where I think that you really could do this even without having done the vector space chapter. Here it says, determine whether or not the vectors listed above are linearly independent or linearly dependent. Now here, so to see whether they're linearly dependent, we need to find a relation of linear dependence. Now, if I go back to the chapter on linear dependence, here it says that vectors are linearly dependent if and only if they have a relation of linear dependence, like this. What does that mean? That means I can take some linear combination of the vectors and get 0. Okay? So if we go to this situation here, I have u1 plus u3 equals u2 minus u4. I can rewrite that as, I can put everything to the left-hand side. I can rewrite that as u1 minus u2 plus u3 plus u4 is equal to 0. Now this is a relation of linear dependence. So that means that they are linearly dependent. Okay, that's all there is to that first problem. Now, what's the non-trivial linear relation? It's right here. 1 minus 1, 0, 1, 1. Now, you can have zeros, that's okay. But this is still a non-trivial relation of linear dependence. Now, some people wanted to say, well, the first 4 are linearly dependent and the last 2 are not. That's not what you say. Linear dependence is a property of the set. If I have any kind of relation of linear dependence, the set is linearly dependent. You don't talk about individual vectors being linearly dependent. You talk about a set of vectors being linearly dependent. Okay, so in this case, here's a non-trivial relation that relates the different vectors.